Hello, everyone. I hope that you are not tired, have had a good winter so far, and also have had the chance to participate in some of winter activities like ice skating and uh, snow skiing. And I think that, but we should also be thankful of our heating systems that keep our buildings warm enough that we feel comfortable. And I think this brings us to the topic of my today's discussion, that is about the uh, amount of significant energy that we need for for making our buildings warm or cool in Canada. And by knowing the fact that we have huge temperature fluctuations in Canada, sometimes in winter the temperature reaches to minus 25, and in summer it reaches to 40, 45. So we see there are many fluctuations that we need a significant amount of energy to respond to this requirement. And here I have brought two pie charts that show interesting statistics about Canada. So here we see that about 4% of energy that we use in our residential buildings, we use it for space heating. And for this energy, we use 55% is coming from burning natural gas that causes to emit 25% of national greenhouse gas emissions in Canada. So this shows that we need a cleaner solution to heat and cool our buildings. And so a promising solution is using the ground source heat pump systems. These systems use the consistent temperature that can be found just a few meters below the ground, and just by circulating a fluid that can be water mixed with some antifreezes, we can transfer heat from the ground and heat or cool our buildings. These systems are efficient, they are very efficient, and they use electricity, and so that makes them better alternative to fossil fuel systems. So these systems have three different parts: the ground loop that is circulating water inside the ground and then brings up. So by this circulating water, we can exchange heat with the ground and with the soil. And the second part is the heat pump that is basically transferring heat from the ground to the building or from the building to the ground. And they have temperature limits. These temperature limits can be 0 degrees C or 35 degrees C. And the third part is the distribution system that is in our houses. It can be some forced air system or radiators or underfloor pipes. So by doing that, we transfer heat from the ground to heat our buildings in the winter, or transfer heat from our buildings and then inject it in the ground and store it there in summer to use it in the winter. So what I do at TMU, I design the first part, the ground heat exchangers. And the ground heat exchangers, they have two types, vertical and horizontal. The vertical type that is called as borehole, they have different types. Boreholes are highly efficient, and because they take less space, but they are also costly. And you see different types of boreholes here. But because they are costly, we use them, but that stops using them because of the cost. And what we are doing at TMU, we are using a new type of ground heat exchanger that uses the helical steel pipes. And we are using the helical steel pipes in our buildings right now to support the structural integrity of our buildings. And so when we have them, why don't we use them also as ground heat exchangers to extract heat from the ground and then use it for heating of our buildings. These ground heat exchangers are shallower, and because we use them for two different utilities, we can decrease the cost. So here I have just compared two designs of boreholes with helical steel piles. You see that the helical steel piles are shallower, and instead of the boreholes that they have U-tubes, they have a pipe that they just send the water to the bottom of the pile, and then the water has more time to come up, and by doing that, it has more time to exchange heat with the ground. So this makes them more efficient compared to U-tubes and boreholes. And here, what I've done to show you how we designed them, I've brought a case that has 6 piles, 2 by 3, that are spaced 5 meters apart, and considered 4 different lengths for these piles. And here we see that the outlet temperature of these piles, how it varies through a year, through the first part that is winter, and then summer, and winter again. And you see that the outlet temperatures are different for different heights of the piles. Thank you very much.